So we're going to pick up where we left off on electronic structures. Okay, and orbital shapes. We said an S subshell has one orbital, holds 2 electrons. A P subshell has 3 orbitals. Each one holds 2 electrons for a maximum of 6. A D has 5 orbitals, maximum of electrons 2 per orbital for a total of 10 electrons. And what's not on here is an F, which has 7 orbitals for a total of 14 electrons. So there's math involved that tells you, it says, reach down. Okay. Different shapes. The s orbital is a spherical shape. So the 2s is a bigger sphere than the 1s. So if I describe an electron in the 1s, I know it's somewhere within the small sphere. If I say 2s electron, it's somewhere within the larger sphere. And a 3s would be even larger, and a 4s would be even larger. If I said a P subshell, 2P, you see they're dumbbell shaped. And there's 3 of them, one along each axis, the X, the Y, and the Z. So the last figure here is all 3 of them put together. So if I said, oh, the electron's in the 2P subshell, you know it's somewhere within one of these dumbbells. 3P are dumbbells, but they're bigger dumbbells. And 4P are even bigger dumbbells. So the electron configuration, okay, we're going to describe where an electron is. Its individual address, like an IP address, so I can tell you, somebody can tell where your computer is located from its IP address, or your phone. Okay? So how do we do this? We start filling them up from the lowest energy state to the higher energy state. And I'm going to go back to this and insert blank page. And split it. So I'm going to write the little map. It's in one of the videos to show you how to do it. So if you follow the map, not a problem. Lowest energy, 1s. Next one we have 2s P, 3s P D, 4s T D F, 5s T D F. Theoretically, there's a G, but we won't get to the G's. 6s T D and F. So we're going to start filling out with the lowest energy first, which would be the 1s. So we follow this red line, so we can go to the 1s. Oops, here to the 1s. We're not going to hit anything in the next line, so we come back up to the top. We go through the 2s. We don't hit anything, we come back up to the top. We go through the 2p, then the 3s. We're not going to hit anything, we come back up to the top. 3p, you'd say next 3d, no, you keep going. 4s. Then you come back up, 3d, 4p, 5s, then you come back up, 4d, 5p, 6s, come back up, 4f, 5d, 6p. So if you follow the red trail, you can do all the electron configurations. What you have to remember, S is how many electrons total? 2. P is 6. D is 10. And F is 14. So let's take a pretty good size element. Let's take tungsten. How many electrons in tungsten?
74.
What was it?
74.
74. Same as the atomic number. Remember, the atomic number is the number of protons and the number of electrons. Oh, it's going to take forever. So, where are we going to start?
1s.
1s. How many can we put in there?
2.
What's next?
2s.
2s, 2. 2p6. I'm going to keep a running total. So far we have 10 up to this point. What's that? 3s, 2. 3p. How many? 6. What's after 3p? 4s. Very good. How many?
2.
Okay, after this point we have 20. After 4s,
3d.
3d,
10.
10. So we got 30. Okay, I'm going to come down here after 3d, 10.
4p.
4p,
6.
6. So we have 36. After 4p, 6.
5s.
5s. So we have 38. After 5s,
4d.
4d. How many? 10. All right, now we're up to 48. We're getting there. 4d,
5p.
5p. How many?
6.
Okay, we're up to 54. After 5p,
6s.
6s2, so we're up to 56. All right. After 6s,
4f.
4f. How many?
14.
14. So now we're up to 70. After 4f, what comes next?
5d.
5d. How many?
4.
5d4. So that makes us 74. Wow. It was a long way to go, but it wasn't any problem if you follow the map. So now we know where all the electrons are located. Good.
Can I ask a question? How come 5D is 4? I'm catching on slow.
How many can we put in a D?
D, I thought was 10.
You could put 10 in, but we put 70 electrons. We only have 4 left. So we didn't fill up that last subshell. I mean, we can only put in what we have. So when you do these, I highly recommend you keep track of the total as you go along. So when you add up the subscripts, it should end up with the total you want. So let's look at 2. Here, erase this part here, okay? Two smaller ones here. Oh, my pens are. And sodium, Na, how many electrons?
11.
11. So it would be electron configuration.
1s. 2 electrons.
And what's next?
2s. 2 electrons.
What's next?
2p.
How many?
6.
What's next? 3s1. It adds up to 11. What's the element right underneath sodium? Potassium. How many electrons? 19. Whoops, 19. Let's do this one.
1s.
1s,
2 electrons. 2s.
2 electrons,
2p.
2p,
6 electrons.
whoops, 2p6, 3s, 2, 3p6, what's that for 3p?
4s.
4s, 1. All right. If you look at these two, sodium ends in 3s1. What period on the periodic table is sodium in? 3. What column is sodium in? 1a. Okay, we look at potassium. It ends in 4s1. What period is potassium in? 4. What column is it? 1. So if you look at your periodic table, how many representative or main group elements are on the left? How many columns? 2, 1a and 2a. How many s electrons are there? 2. Everything in column 1 is going to end in S1. Everything in column 2 ends in S2. So I can look and say rubidium, Rb, is going to end in 5S1. It's in period 5, column 1. Calcium is going to end in 4S2. Look at the other main group elements on the right. How many columns are there? 6. How many p electrons are there in the maximum? 6. What a coincidence. So I would say column 3A would end in P1. Column 4A, P2. 5A ends in P3. 6A ends in P4. 7A ends in P5. And 8A ends in P6. Now, let's look at the transition metals. How many columns? Columns, the transition. The transition are the ones in the middle. No, not the bottom.
No, not that.
10. How many d electrons are there? 10. Another coincidence? I think not.
You said D electrons?
D. Now, so row 4, what is the first principal level that has D electrons in it? From our map, what's the first one that has a D? 3. So the top row of the transition are going to be 3D, even though it's in row 4. So it'd be 3D1 through 3D10. Second one would be 4D, 1 through 4D10. The next one down is 5D, 1 to 5D10, and 6D to 6D10. When we did, which one did we do? We did tungsten. Tungsten ended in, if you remember, write it down. What? 5D4? Okay, so if we count down from chromium, that's 3D, 4D, tungsten's in the 5D row. Count over, 1, 2, 3, 4. 5D4. I didn't have to go through all 74 of them to realize it ended in 5D4. Just look at the periodic table. Intertransition elements, the 2 rows that were taken out on the bottom. How many columns are there? Take a wild guess. 14. How many F electrons are there? 14. Remember at the beginning of the semester I said there was another reason they took those 14 out? So guess what they're going to end in? F1 through F14. Which is the first level that has F electrons? 4. So the top of the top row is going to be 4F through 4F14. The bottom one's going to be 5F1 through 5F14. Okay? Yes?
So you're calling the D with the 10 the transition. So what do you call them, the first 2 and then the...
Those are the main group. The first 2 are the S's.
Which are the main groups?
Those are the main group. Remember?
Transition.
And the last 6, all the ones that are marked in A's are the main group. If you look at their numbers. So 1A and 2A are the S electrons. 3A through 8A are the P electrons. 3B through 2B, the transitions, are the D electrons. And the bottom 2 rows are the F electrons. There are a couple exceptions. We're not going to get into them because it has to do with a lot of really close calls. So just think about it. Like chromium's exception, copper's an exception. I'm not going to bother explaining why.
So what are the 3A and the 8A called? You have the main group transition, and what's the
The 3A,
the
the main group are the 1A, 2A, 3A, 8A. All of those are the main group. The rest are transition and intertransition. Okay? Actually, I'm going to keep this in this mode. So this is kind of how we're filling it up too. And this is another way of drawing it, where they draw little lines to represent the orbitals. So S only has 1, E has 3, and D would have 5 of those little lines. And each line can hold 2 electrons. So if you prefer to do it that way, you can do it that way. If you just follow the map, you can do the map. And that map is in one of the videos that I posted too. I think I put that up on the board last time for you guys. So now they're just going through a couple here. And move my little recording device thing so you can read that. Maybe I'll put it down here. Valence electrons. I said all the chemistry occurs with the electrons. What occurs with the outermost electrons? Those are called the valence electrons. They're in the valence shell. Those are the shell. You look when you do the electron configuration, the highest number. So beryllium, the highest number is 2, has 2 valence electrons. Chlorine, what's the highest number in chlorine? Here's the electron configuration. What's the highest number? 3. Well, there's 2 electrons in the S subshell, 5 in the P subshell. You have to add them together. So chlorine has 7 valence electrons. All right? Always look for the highest number. Yes, we did tungsten, and we had a 6s2, then we went back to a 5d. The highest number was 6. So those are the valence electrons. You can either do the electron configuration, I will tell you an easier way to do it, going back to your periodic table. Column 1. 1A has 1 valence electron. Column 2A has 2. Skip the transition, they're a little funny. Column 3A has 3. 4A has 4. 5A has, got the pattern? 6A has 6. 7A, 7. And 8A has 8. So now you don't have to do all the electron configuration because we're really interested in the valence. I mean, you have to do it on the test, but you don't have to do it to do chemistry. We're interested in the valence electrons. So, elements in the same group have similar electron configuration. We did that, and I showed you sodium and potassium. They had the 3s1, 4s1. Elements in the same group have the same number of valence electrons. The only exception in column 8 is helium. Helium only has 2 valence electrons. Because helium only has 2 electrons. You can't have 8. So helium is fine with just 2. So the chemical properties of elements in the same group are similar because they have the same number of valence electrons. If they have the same number of valence electrons, their chemistry is going to be similar. Okay? Makes sense? Because later on, chemistry is basically doing stuff with the electrons. If they have the same number that we're using, it's going to be similar. The only difference is, like for sodium and potassium, they both have 1 valence electron. Sodium, it's in the 3s subshell. Potassium, it's in the 4s subshell, so it's farther away. So they're going to act similarly, but not identical because one's a little bit farther away. So this pretty much shows you by the periods 1, 2, 3, 4, 5, 6, 7, 8. So if I ask you how many valence electrons sulfur has, you should immediately say, or you just jump out with it. 6. It's in column 6. And don't be afraid to make notes in your book on the periodic table, valence electrons, and then later on when we do charges and that. So when you look at your periodic table during the test, you go, oh, boom. So if I said carbon, valence electrons, 4. It's in column 4, carbon, C. Yeah, you kind of got to know the elements.
Yeah.
So on the back of the periodic table, oh, maybe not, yeah, on the back, is a list of everything in alphabetical order, so if you have a problem, you're not sure, you can go down and say, oh, carbon, symbol, C, not CA,
Yeah, that's funny.
okay? And you'll get the hang of it after a while. Some of them, we'll use a lot of the same elements because we aren't going to get into a lot of the fancy ones. We can represent valence electrons, which are called electron dot symbols. All right, let's not make this any more complicated than it is. Actually, I'll write on the chart here. So, sodium, how many valence electrons? One. One dot. Carbon has 4 valence electrons. If you think of each atom as having 4 sides, when you start putting valence electrons, you don't put them in pairs, you keep them apart. For example, magnesium has how many valence electrons?
2.
So you do 1 dot here, 1 dot here. Now it doesn't matter, you put them opposite each other, or you put one on top, just keep them separate. So after carbon, okay, you got all 4 sides have 1 dot. If you go to oxygen, which has 6, then you got to start pairing them up. Chlorine has 7 dots. Ultimately, you're going to end up with column 8, which has 8 dots, so it's 2, 2, 2, 2 on each side. So the dots just represent electrons. Where am I? What about trends in the periodic table? What else can we find in trends in the periodic table? The ionization energy. That's the energy needed to remove an electron from a neutral atom. So, we'll look at sodium. How many valence electrons? 1. All right. So here we have sodium. She's the nucleus. So here's her valence electron. Hold on to it. I want to pull it away. It's going to take a certain amount of energy, right? Not too hard. So it takes a certain amount of energy, right? Potassium. How many valence electrons? 1. But it's not in the 3s, it's in the 4s. So its electron, its valence electron's a little farther away. So is it going to take more or less energy to pull it away from the nucleus? Less. How farther away? Nucleus is what charge? No, nucleus is not neutral. Nucleus is positive. The electrons are negative, so there's an attraction, right? So the closer I am, if I'm an electron, the closer I am to the nucleus, the more attraction there's going to be. So to get me away, I have to pull harder. If I'm already farther away from 4s, it's not going to take as much energy. If I'm at the 5s, it's going to take even less energy because you're way over there, and I'm over here. Okay? So as you go down in a column, the ionization energy decreases. As you go from left to right in a row, it increases because you now have more protons in the nucleus as you go from left to right. So now you have more positive in the nucleus, so it's even stronger attraction.
So left to right in a row, the energy increases, and how does it decrease again?
Top to bottom.
Top to bottom?
So let's think about this in terms of reactivity. Let's say to react a metal from column 1, I have to remove that valence electron. So if we look at sodium, potassium, rubidium, which one's going to be easiest to remove the electron? Rubidium, because it's further down. So which one do you think is going to act faster, react faster?
Sodium?
Rubidium. If I have to remove the electron to get it to react, which one requires less energy to remove? Rubidium. So it's going to react faster. Make sense? Okay. See a lot of deer in headlight looks. Sodium. There's her electron. Potassium. Here's his electron. Okay, coming over here, I have rubidium. Here's her electron. It's farther away. Farther, farther, farther. I want an electron, so I got to take it from somebody to react. I go up here to take her electron. What's she going to do? Man, he's got to reach out further, but I could still, it's easier than... Poor her over here, no problem. Hers is way out here. I got that sucker. Okay? So that's a lot easier to react than that, Okay? Yes?
You're essentially talking about like compound elements, when elements combine.
Yes, when we're talking about
You go
making
from a single
compounds.
element to compound. Okay.
Yes.
And the outer valences, like the outer ones closer to each other will combine. Like,
Not quite.
okay.
But we're talking about the outer ones. So, skipping ahead a little bit,
Don't do that.
we said sodium has one valence electron. Chlorine has how many? Seven valence electrons, not total electrons. Everybody wants to have 8. Now remember, sodium has 1 on the end, but it has 10 underneath. Sodium has a total of 11 electrons. We look at sodium, it's 1s2, 2s2, 2p6, 3s1. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. 3p5. 17. So, sodium, if it gets rid of its 3s1 electron, okay, it becomes 1s2, 2s2, 2p6. What is the total number of valence electrons there? 8. We have 2 here, 8. So it has 8, which is what it wants. Everybody wants to have 8. So this becomes Na plus what? It has 8 valence electrons now, because I got rid of the 3, so now the 2's become the valence electrons. So I have 8. So I'm happy. And because I lost an electron, I now have a positive charge. So I have more protons than electrons. Chlorine has 7 valence electrons. It wants to have 8, so it's going to... It needs 1, right? So if it gains 1, it becomes 1s2, 2s2, 2p6, 3s2, 3p6. Again, a total of 8. Since it gains an electron, we now have Cl minus. It has 1 more negative charge than positive charge. If you lose an electron, you become more positive. If you gain an electron, you become more negative. So now, let's look about it. We have sodium and chlorine together doing a reaction. Chlorine over here wants an electron. I'm sodium. I want to get rid of one. Wow. What a happy coincidence. Here you go. I'm happy. He's happy. He has a negative charge. I have a positive charge. Now what happens? We attract each other. So now the result is sodium chloride. Kind of skipped ahead a little bit when we talked about bonding, which we're going to get into, but that's how chemistry works. Column 8 is the key. The noble gases. Everybody wants to be like column 8. And there's a couple ways to do that. Once you figure that out from the valence electrons and that, it's pretty simple.
Yeah, I heard that before.
Okay. Here, and that is 38 electron configuration, first row elements.